Okay, today we're going to be looking at the titration curve of a strong base titrating a weak acid, which is a little different from titrating strong acid and strong base. The shape is a little different, and I want to pay particular attention to the particle model of what's going on during this curve. So the acid that we had in our lab was acetic acid, which is this formula here. Typically, this is a long formula to write, and when we have some kind of weak acid, we can abbreviate that HA, H being the H plus proton, and then A is part of the acid. So these two ions are stuck together, and what we're going to have in this beaker here, so this is our beaker of weak acid. Nothing is being titrated yet. This is a 0 NaOH has been added. So in this beaker here, my weak acid does not dissociate hardly at all because everything wants to stick together. And then we have our weak acid molecules. So I'm going to start with 6 of the molecules here. And this weak acid, as we've talked about in this class, we have HA, and if it's sitting here, not reacting with anything, it's going to be in equilibrium, and that's going to break up into H plus and A negative. So my Ka for this, remember my equilibrium constant is going to be products over reactants, so H plus, A negative, all over HA. Okay. So the question now becomes, well, what happens when I start adding NaOH to this beaker? What will happen to the solution? What will happen to the pH? What will happen to the mixture? And let's take a look at that. So point 2 of the titration curve is when a little bit of NaOH is added. So I'm going to take, this is just partway down the curve, and so I add a little bit of NaOH. So my reaction here, well, the only thing that's going to be reacting is the OH. Na is always a spectator. So I'm going to take my HA and react it with my OH negative. And what is that going to form? Well, remember, OH is going to react with my acid and form water. But now it's not just water, because this thing is going to be left behind. This OH is going to pull this H plus off, and I'm left with an A negative. So when I take this beaker here and I add OH minus, I'm also going to add Na plus because the Na has to be there. I just want to show it where it's going to be. So when this gets in here, what's going to form? Well, I will still have majority of my acid. So my HA, I still have a bunch of these. I'm going to write them a little smaller so I can fit everything in here. Okay, so I have 5 of these in here. But then one of them is going to form a water. So I form a water. And then I'm also going to have a negative remaining. And I have an Na plus as my spectator. Okay, so in this, if I look at my ratio of how things are set up here, I have, well, my Ka, I'm gonna write my Ka again. My Ka is always gonna be H plus, A negative, all over HA. But now I have A negative and I have HA in here. And when I have both of these things in solution, This is now called a buffer. So a buffer is any solution that has, for a weak acid, a buffer has to have HA, the acid, and its conjugate in solution. So A negative, which is the conjugate. Okay, so a buffer is the acid and its conjugate, or if you look at bases, the base and its conjugate, but a buffer has to have both things in solution at the same time. I have a lot of HAs in here. I have very few A negatives, but there are some A negatives. And so if I look at my ratio of these two things, I still have a lot. This thing here is big. This is going to be small. And so in order for Ka to stay the same, because Ka remains constant the whole time, it's an equilibrium constant, this H plus here, in order to balance this out, this H plus is still gotta be pretty big. Okay, so I still have a lot of H plus, and it's still acidic. Remember, so if I look at my pH, down here, it's an acid, still an acid, still pretty acidic, so this H plus is gonna be a little bit bigger to make this all even out, okay? So we're gonna keep looking at this ratio as we add OH minus to this. Well, what happens when I keep adding OH minus to the point where half of my acid molecules are reactive? So now I'm gonna take 0.3 of my curve. I'm gonna keep adding OH minus until I hit this point. And so what's gonna happen? Well, remember in point 2, I had this picture, but I'm gonna add more OH minuses, so Na plus and OH minus. I'm gonna keep adding some more until half of this is gone. And let's see what happens. So I'm gonna have half of my acid still remaining. I have 3 water molecules now because these OHs are gonna react with these over here. So I'm gonna have 3 water molecules, so water times 3. And then I'm gonna have 3 A negatives, so A negative times 3. And then I also have Na plus times 3. Well, what's going on now? I've got 3 HAs, I've got 3 A negatives, so I still have a buffer, because by definition, I can have, I have to have the acid and its conjugate. And what's my ratio now? Well, Ka, remember, is H plus, A negative all over HA. And if these are the same, so if HA and A negative are the same, well, what happens to this expression? These actually cancel out. So at this point, Ka is equal to H plus. And this is called the half equivalence point. So the Ka equals H plus. If I wanted to figure out what the Ka is, all I need to do is figure out what the H plus is. Or the same way, I can actually take these things. I'm running out of space here, so I'm gonna write it up here. And if I write and took the negative log of the Ka, that equals the negative log of H plus. And that is equal to what we call the pKa. And that's equal to pH. So something called the pKa could be figured out at this point. And the pH, if you know the pH, you can actually get the pKa and then work your way backwards to get the Ka by taking, you can do 10 to the negative pKa to get the Ka. Okay? So that's a very unique point. It's very important to know this point. If we march a little forward, and we're going to go on to point 4 now. So point 4 is just a little bit past the half equivalence point. What will happen? Well, I think you're starting to see a pattern here. we have 0.3 here where everything is equal. If I add another OH minus and Na plus, that's gonna give me another water. So I have HA, HA. I'm gonna take this and make this into another A negative. So I have 4 of them now. I'm gonna make another water, HOH times 4, and then I have Na plus times 4. Okay, so now my A negative is overpowering my HA, and it still have a buffer, but now my buffer is shifting a little bit. So if I look at my H plus, A negative all over HA, and I can see that this number here is bigger, and this one's getting smaller. So therefore, in order for this to stay a constant, my H plus is gonna be getting a little bit smaller, okay? And as I keep adding base, it makes sense that my H plus decreases because I'm making it less of an acid. Until we get to 0.5, which is the magic point. This is the equivalence point. So the equivalence point is where everything is reacted. And so if I'm going from this 0.4 to 0.5, well, what happens there? Everything reacts, so I'm gonna add enough OH minus to get all my HAs away. So now I'm gonna have water times 6, I have 6 waters. I have A negative times 6, and I have Na plus times 6, okay? Na plus spectator. So what's remaining? Well, I have some A negative here. I also have water. And if you recall from the titration, this pH is not at 7. It's above 7. So why is that? Well, at the equivalence point, the A negative is going to do something. So A negative, if it is with water, okay, remember A negative is not just any spectator, it's conjugate, and it's actually going to react with water. So water is going to say what we call undergo hydrolysis. So hydrolysis happens, which means that water breaks apart. And when A negative reacts with water, it's going to form, well, it's actually going to form HA again, plus what's remaining? OH minus. And because we have OH minus in solution, well, whenever OH minus is in solution, this is a base. It's a strong base. It's hydroxide. That's going to push my pH to be greater than 7. So it's really important that when we titrate a weak acid with a strong base, we're going to be left with this A negative at the equivalence point, forming OH minus, and that's going to make our pH above 7.